Wonderful. Yeah, video was promised because yesterday went poorly. Um, I have a lot of questions to go through and not much time, so you're welcome to play back at half speed, make judicious uses of pauses, etc. And as always, you can reach out if you have any questions. Could you find me a? I remember the first question from the first take was the z-scores. As always, normal distribution. Z-scores from the table. This table, from the table. Point 1, point 2, etc. 0, 0, 0, 1, 0, 2, etc. And there's a table, and you find, the value. And as we remember, z-scores are always the area less than or equal to the given value, as we remember. Negative infinity to z of stuff equals the percent that we want. And from that, we can either read directly if you need less than, or if you need more than, remember 1 minus by complements. This question is fairly straightforward because we spent a full week doing it. Moving on, can you just, whichever one the next question is, it's the one that doesn't look like a slide, so it'll have that little dialogue box, so when you scroll down, like that has the slide, that has the dialogue. Yeah, okay, cool. There we go. And this one on bootstrap distributions was where we left off yesterday when I got fed up with the software. But now I am back in my proper element. Consider the following bootstrap distributions. Right skewed sample of n equals 10. Mean is, let's say 16. That says 16. With mean is 16. And then n equals 50. Mean is 16. And if I remember correctly, it was yes. Which of the ones are true? So let's go through it. First of all, means are still going to be 16. When we take a whole bunch of bootstrap sampling, the means are going to be roughly 16, as we learned in chapter 1 and reviewed in chapter 17. However, for skewness, n equals 10, I believe, is more likely to be skewed. You're welcome to click show correct answer, because while I am 99.9% certain on everything, it turns out 100% is important. Good, I'm correct. I love that. N equals 10, more likely to be skewed, and the reason for this is because there's a smaller sample size, so when you're bootstrapping, no, that's just too many dots. When you're bootstrapping, right, this isn't exactly 10, but it's a small sample size. We take this, it's already going to skew our average distribution, right? Center 16, long tail. When we go 50, we still have this thing out there, but we have a bunch more here that are more likely to be observed, and as such, it is less likely to be skewed, and it will still have a mild skew. It'll be approximately normal, but unless we take infinite observations, it will never be literally normal. But for our purposes in Stat 121, approximately normal is approximately good enough. Moving on to, yes. Right. More likely to produce the estimate. And this was what I was trying to go over in class, but I couldn't figure out how to use the thing. So, any distribution. And I'm going to take, we have our normal distribution. I'm just going to leave it up here. We take any distribution. I'm going to make it uniform, as anti-normal as possible, right? Any distribution. Everything is equal chances. And we start taking values. And we take a value. And we have a mean. And now we take another value. And the mean shifts over here a little bit. The mean goes all the way here. The mean goes back, and so on, and so on, and so on. Notice, as we are taking more and more values, the mean doesn't oscillate as much. It starts concentrating all the way here, here, and eventually, if we took, say, infinite values, the mean would just be our mean of the distribution. All right, now we will extrapolate that a little bit. The mean at, say, n equals, let's say 10, n equals 50 observations is going to be, very wide tail. Wide tail. The mean is going to be the same as the mean in our original distribution, no matter what, by the central limit theorem, which, as I said, is possible to prove, but we don't go into that here. As we go closer to 200, though, it's going to start concentrating because our extreme values will start getting outweighed by all the values in the center. And of course, infinite is just that. As we learned in the central limit theorem, our sample mean is going to approach our population mean, but our sample standard deviation is going to approach population standard deviation divided by root root n, yeah, divided by root n. As sample size increases, the standard deviation of our sample mean is going to decrease. What this is graphically is it gets more clustered around the actual value. So 200 is more likely to produce a sample mean. Thank you. Thank you very much. And see, this is why I have someone here to help me, because all those seconds I would waste would add up. Moving on. Distribution of a sample mean will be normally distributed. And first of all, again, but approximately normal, and there are some rules of thumb. And if I remember correctly, it is either the sample size is at least 30, or the population is also normally distributed. And I could explain, but there was a lot of math that will be required, so instead I'm just going to say this is what it is and learn it. And if you're really curious, I guess you could look it up. But it would be difficult. Distribution of the sample mean will be all the situations shown below except part A, sample 12 from the distribution from a normal distribution. So we're sampling 12, but normal. So our distribution of the sample mean will be normally distributed. So A is it's except, so A is incorrect. B, sample 40 CEO salaries, normal, who knows? But 40 is greater than 30. So this is still going to be normal of the sampling mean. Part C, sample 24 rent values from the distribution of rents. And capital N, of course, here being normal, little n being sample size. Here, less than 30, and we don't know if it's normal. So part C, we have no way of knowing if the distribution of the sample mean will be approximately normal. And obviously then the correct answer is C, but I'm going to go on and cover D because we're learning. Sample 32 verbal SAT scores. So here, n is over 32, and it's normal. So obviously normal. What's this next one? Oh, histograms. And you will see on your screen under properties of sampling distributions a bunch of histograms. And it will depict, one of them will look like this. One of them will look more like this. And scroll down, thank you very much. One of them will look like this. And these drawings are terrible, but you will have it on your screen. And it says the distribution of the, oh wow, that has some skew. One of them will look like this. Ooh, boy. And which of them distributes the distribution of the original population? So this would be impossible, except we know that one of them is original. We know that one of them is sampling distribution small n and sampling distribution large n. So as n gets large, our variance decreases. This has a tiny variance, these two not so much. And then we just think, this one looks more normal than that. And the distribution of the mean is, even for a non-normal distribution, is always going to be more normal for any sample size greater than 1. And then that can be proven. And I'm not going to do that. This long skew, as we see in our histogram, gets eliminated when we move to the mean. The correct answer is the second circle. And again, I'm moving very quickly. By design, we have limited time. I would strongly suggest slowing it down or pausing regularly. Next question. Oh, I shouldn't have erased those histograms. Well, with the same logic that I already used, I think it's the third one, right? Yeah, it's the third one. Same logic I already used in the previous question. Let's just move on to the next one. I'm too lazy to redraw it. Distribution of sample mean 1. Mean annual income, all right, mean annual income is 542 grand, 542 G's.
No, it's just 42,000.
Oh, that's a dollar sign.
Yeah.
Thank you. Mean annual income, dollar sign, 42 G's, 42K. And our standard deviation is, that's going to be 30. 30K. That makes sense. Much more reasonable income. Our researcher draws a random sample of 900 city residents. To interview, what will the mean? The mean. What will the mean be? Well, the mean is the mean. And when we take a value, it will still cluster around the mean. The sample mean distribution is going to be narrower than the original population distribution, but the mean is still going to be centered at the same place. So it should be 42,000, not 542,000, but rather 42,000. Moving on, please. Now this should be the standard deviation, right?
Yeah.
Yeah, standard deviation of the sample mean distribution, if I remember correctly. Yep, sampling distribution of the sample mean. Here we use our formula that the variance defined to be, and I'm gonna use variance on purpose because it makes it a lot more a lot easier to understand when we use variance, okay? Mean, mean. Variance, notice square, variance, population variance over n. Divide by the sample size. That way, of course, when we square root both sides, that is where the square root term comes from. If you were confused, why do we divide by the square root of n? Why don't we divide by n? Remember, everything normal distribution is defined by variance. We use standard deviation to make it easier. So actually, we are dividing by n. We're just taking the square root in the stuff that is useful for people to understand. But this is where it comes from. And we take, and we take 30,000 and we divide it by the square root of 900 and we get whatever we get. Moving on. As you know, I don't care about the numbers. Moving on to, ooh, that's fun. Oh, this is population proportion. Ooh, so if I remember correctly, we're gonna want, either, of course, the population is normal, right? Population is normal, or, NP and n1 minus p greater than or equal to 10. So we're going to want the amount of, this is the sample size times the proportion. So this is the number of things we have in the sample, number of things we don't have in the sample, and both of those need to be at least 10. Again, math. And we will skip the math. And we look at sample of 30 from a population with p equals 40. I'd say normal. No, it's p equals 40. Yeah. What was I going to say? Oh yeah. So we do 30 times 0.4, and that's greater than 10. And of course, 30 times 0.6 is also greater than 10 because if the smaller one is greater than 10, the bigger one is also. Sample of 50 from a population p equals 0.9. 50 times 1 minus 0.9 is less than 10. This is not going to be normally distributed. And we continue on the list, and by the same logic, C is normally distributed and D is not. Moving on. What's my time looking? Okay, time is looking good. 10% of people are afraid of flying. All right. Proportion. 10%. 0.1. If we take a sample of 100 people, and we determine the proportion who are afraid to fly, the sampling distribution will have a mean equal to, again, mean is going to be the same regardless. So the variance is going to shrink. Mean is a mean proportion. I don't remember the symbols. This is awkward. But I'm going to just write mean proportion. This is probably the wrong symbol, but I am saying it out loud. Mean proportion, use the correct symbol, is going to just be equal to the sample's mean proportion. So I don't know. But the means is going to be the same. It's going to be n times p, which in this case is going to be 10. 100 times 0.1 is 10. Oh, that's helpful. Oh, that makes sense. Mu being mean, p hat being, thank you very much, being observed proportion. Much appreciated. Thank you. Yeah. Good. But it will be equal to NP 100 times 0.1, which is 10. Standard deviation is square root of proportion 1 minus proportion over n.
Yeah, that's right.
That's right?
Yep.
Yes! Memorized. Let's go. This is something I haven't done in years, so I'm kind of proud of myself. But it's good that I memorize it because I'm not telling you the wrong thing. This proportion 0.1, thank you for checking my work. N, 100. We plug it in. We get a value.
That value is...
That value is 0.03. That makes sense. That's the value.
That's it.
Oh, that's it. Okay, what else was I going to do? I was going to do reading questions 6 and 7 from the reading because someone asked me personally, and then I was going to give hints for the homework problems. And Dr. Park would frown on me if I solved the homework problems before it was due, but there will in fact be hints. Yeah, reading questions 6 and 7. There it is.
Is this it?
Yep, looks right. I'm too lazy to edit that out of the footage. A sample size of 120. Sample size of 120. will be drawn from a population with a mean of 18. Population mean mu, Greek letters. And standard deviation of 4.2, sigma, Greek. What is the mean of the sampling distribution? Sample mean. And 7.7, I presume, it is in fact sample standard deviation. I will, again, remind you, variance, 4.2 squared. Normal, always, normal, always mean and variance. Why am I blanking? So the mean, as we know, x bar equals mu equals 18. All right, x bar equals mu, and think about it. Population, okay? I take, can you just make sure this part shows up on the camera, please? It should, right? It does, wonderful. Thank you. I take value, and I average them. And though it's peaked, the averages have the same mean. Pretend these lines overlap. That. And then standard deviation, again, variance, original variance over n. And as of course, s equals the square root of s squared. So we do this, we square root, or, yes, or we do this, sigma over root n. That is, of course, equivalent. And we get something. We get 4.2 over a little bit more than 10. So we get a little bit less than 0.4. A little bit less than 0.4. Whatever it is. But this is the process, right? The numbers are going to be different on the quiz. And then I was going to hint for the homework, right? I don't remember if I was going to do anything else. That's awkward.
There's also this question here.
Oh!
Yeah.
Oh, standard error. Yes, that's what I mean. Standard error. I'm sorry. Standard error. I've been using the wrong term all lecture. Populations have standard deviation. Samples have standard error. That's my apology. Standard error. This, I was not precise enough in my language. I apologize for that. This. That's all it is. It's the same thing though. It's the same. That was the thing we just did with the sigma over root n. But yeah, thank you for correcting me. Standard deviation is a parameter. Standard error is a statistic. Standard error is a good approximation of standard deviation. Yeah. It does say standard deviation. See, that's where I was confused. Presumed. Okay, good. So, upon talking, this is not 7.17. This is based off of 7.17, but it is not problem 7.17. The numbers have been changed. Can you actually get me back to 7.17, please? Thank you. The percent of males, who smoke. Percent who smoke. Ooh, that S is going to be confusing. M for smoking is changed to 20%. Suppose we randomly sample a number, n, that has been changed to 300. Why not? And we determine the proportion who smoke. The sampling distribution, yes, good. An exact answer for the mean. Again, the mean will be the same. The mean will be the same. Our mu p hat. Yeah, mu p hat. Still 0.2. Proportion 20%, which as we know, 0.2. Remember, if you put in 20, that is wrong. The proportion is never going to be more than 1, so probability. So remember, 20% convert to 0.2. And, oh yes. Standard deviation, p hat. Let me change this. Variance p hat. Proportion, 1 minus proportion over n. All right? This means standard deviation p hat. Square root. Voila. And proportion, 0.2. Obviously, 0.8. I'm not going to go into that. And 300. And what we do here, multiply, divide. We use this, because I cannot do this in my head. We get 0.2 times 0.8 over 300. The variance is something really small. Oh my God. Is something small. The standard deviation, defined as the square root of the variance, is 0.001. 0, 2, 3, and you round to however many decimal places. 4 decimal places. 0.023, 1. And you get that. And this is the process for solving 7.17 on your homework. Do you think I should give hints? Good. All right. So, 20 minutes worth of video. I went very, very quickly. I would advise you to spend maybe at least half an hour watching this, maybe 40 minutes. Shouldn't take more than 45 to an hour. And obviously over several sittings. I'm gonna put this up Saturday, so you'll have plenty of time. No, definitely not Friday. I'm busy Friday. Saturday, so you'll have plenty of time. And I think that's it. Everything else is either stuff from chapter 6 or stuff that I have covered. But as always, you can reach me on GroupMe. You can email me. You can reach me, in class. All that. I hope you enjoy your day. I apologize again for the quality of Wednesday, as I say this is yesterday, of Wednesday's discussion, and I hope this is a worthy substitute. Thank you all for watching. Best of luck on your homework.